Okay, welcome to note set number 3, where we'll be talking about convolution and the impulse response of linear time invariant systems. And you can see that we are still doing review here. You should be reading section 2.3 of Proaicus and Monolacus. We will be getting into new stuff shortly, but I'm a firm believer that before you get into new stuff, you need to go back and review the most important basis upon which we will build, and that's what we're going to be doing here. So ahead, we'll be talking about convolution, which you should have seen before in your studies of signals and systems. And I just noticed here that we should have a y of n there to match what we have over here. But other than that, that should have been obvious that that's what we were talking about. So we've got a system, and we're going to talk about there being the initial conditions set to 0. And in the continuous time version of these things, we talked about that meaning there was no energy stored in the system. If it were a circuit, we'd be talking about no energy stored in capacitors or inductors. If it were a mechanical system, no energy stored in terms of momentum or torque, stored torque or anything like that. In a discrete time system, it just basically means all the memory locations, all the unit delays that are inside the system are set to store zeros initially. And we'll see more about that later, but for right now, let's not get into too much detail about that. But we have all of our initial conditions set to 0. And what we're seeing here is the definition of the impulse response. So it's what comes out of a LTI system when the initial conditions are set to 0 when we put a delta function in. So delta function goes into the system, impulse response comes out. And we're showing a causal scenario here, although it doesn't have to be causal. Convolution works just fine for causal or non-causal. But the system does have to be LTI, as we'll see in just a little bit. So the impulse response is something that we can use to characterize the system. Okay, I seem to be floundering here a little bit with this explain everything. I will try to get back on track here. What I thought was a control to go backwards doesn't seem to be that. But I'm going to... Okay, I think I'm back on track here. So the impulse response h of n uniquely describes the system. And once we know what h of n is, we can use it to completely identify the system and specify how it will behave. And this is true only for LTI systems. So once we know that we have an impulse response, we can almost pretty much just replace the box with an h of n. So when you see a box with an h of n inside it like that, you're essentially being told this is an LTI system. Okay, so what we're going to do here is try to answer what it is that how we use h of n to find the zero state response. So zero state response simply means that we're trying to find the output when the initial conditions or the state of the system is 0. So the answer is going to be convolution, but to see how this actually works and how we get to just do convolution, we're going to go through 3 steps to see how this all works. Once we've gone through these 3 steps, we'll have the answer that convolution tells us how to find the zero state response. We won't have to do these 3 steps every time. We'll just do convolution. So the first step is using the idea of time invariance. We know that since if we put in delta of n, we get h of n out. If we take delta of n minus I, so we're shifting it I positions, what we'll get is the impulse response shifted by I positions. Second step, using part of linearity, and this is what people would call the homogeneity part of linearity. So we're not weighting two different inputs and adding them together. We're just weighting one input. So that's the homogeneity part. So we're going to take a given number I, go and grab the input sample at that instant I, and so there's a single number times a function of n. So the delta of n minus I is a function of n shifted by the single number I. And so the thing that comes out will be the impulse response shifted by I and multiplied by the same number that the input was multiplied by. So again, it's important to remember that x of I here is just a single fixed number. Okay, so to illustrate step number 2, just to make sure that you have a concrete idea of what that's saying, let's take a look at this scenario here where we have a simple 4-sample signal. Now we don't have to deal with any of the zeros before or after, since those will just create 0 outputs. But if we apply this step for I equal to 0, what it's telling us to do is go grab that number 1, multiply that number times delta of n, so we get a 1 times delta of n, which is just delta of n. So the thing that comes out is 1 times h of n. Now let's pick I equal to 2. We go up and we grab x of I for I equal to 1. We go up and grab x of 1, and so that number is 2. So we get 2 times delta of n minus 1. Since I is equal to 1, we're shifting this to delta of n minus 1. And so what comes out is the impulse response shifted by 1 and multiplied by 2, because that was the number that we ended up multiplying. So x of 1 was 2. Letting I equal to 2, we do the same thing and we get 1 of h of n minus 2, since 1 was the value of the input at that value of I. Now we take I equal to 3, we shift the delta function by 3, multiply by x of 3, which happens to be 2.5, so we get 2.5 times h of n minus 3. Okay, so this thing is beautiful now. We've just illustrated step number 2, and then the key thing is step number 3, where we're now going to use the additivity part of linearity. So we figured out in step number 2 that if we put in an input that looked like this, the output would come out like that. And so if we, for all the different I values that we had here, if we put all those in, and we get each one of these things out, let's imagine adding all of these things up. So if we put in this as our input, which is just the sum of all these things for all the different I values, what we'll get out is this thing. But now let's just take a look to see what is this thing that we're putting in. So let's take a look. So the thing that we're putting in, going back to our example here, x of 0 times delta of n looks like that. X of 1 times delta of n minus 1 looks like that. The next term looks like that. The next term looks like that. So those are all of the things that we put in individually, and we're asking to add all of those things up. If we add just down vertically, add up for each value of n, what we see is that we get the actual input x of n. And really, if we look at this carefully, we can use the sifting property to find out that that should sift, or sifting over I, that should sift out the value of x when I is equal to n. And so the result of that sum is x of n. So we now know that this is just a different representation for x of n. And so what we're putting into our system is x of n and out. So this is x of n, goes into the system. We just showed that when x of n goes in, this is what comes out. And so we call this summation the convolution. We notate it with this symbology. And so what we've just shown is that for an LTI system with an impulse response of h of n, the output can be found by just doing this convolution sum. And so that convolution sum is something that we, in the signals and systems class, we spent a little bit of time learning how to deal with that. And I would thoroughly recommend that you go back and do some of that graphical convolution just to kind of remind yourself of how that actually works. So our big picture here, for an LTI discrete time system in zero state with an impulse response h of n, we can analytically find the output by just convolving the input with the impulse response. So this is one way of how we can make sense of how a system will behave, predict what it will do when a particular input is applied, and understand the behavior of systems. So this is our general form, and we didn't show it here, but we talked about it in the signals and systems class, that we can actually write this summation in either of two equivalent ways. And you can see that the role that x and h play in the first one are just reversed in the second one. And so that's an easy way to show how that all works. Continuing on here, if we ask the question, well, what happens to our form? So if we look at this general form, what happens to that form if we can say that the LTI system is causal? Well, if the LTI system is causal, we know that h of n must be, just by definition of h of n and causality, we know that it must be equal to 0 for all n that are less than 0. And so if we go up and we look at each one of these forms, we can see that for that, if we impose this condition that h of n is equal to 0 for n less than 0, what that does is it stops this sum. Instead of having to go all the way out to infinity, it makes the sum stop at n. And we can see why that is. Let me just see here if I can get back to get rid of some of this stuff here. The reason that is we can see that in this form, when I gets so large, gets larger than n, we get h of something negative. And so then h would be 0 and no reason summing up all those terms. Likewise, in the other form, we would truncate the sum on the other side. So that's if the system is causal. What if the system is not necessarily causal, but on the other hand, the input starts at n equal to 0? So that's a scenario that we like to think about a lot. We've got a signal, it's 0 up to a certain time, and then suddenly we start applying non-zero values to our system. Well, following the same kind of interpretations, in one form we will be able to truncate the sum at the I equal to 0 point, and with the other form we'll truncate it for the I equal to n point. Now, if we combine both of these situations, we have a causal system and the input starts at n equal to 0, then we get a scenario where both truncations occur in either form. So this is a scenario that we're going to use a lot. Occasionally we'll have to use the most general, and occasionally we'll use one of the intermediate results, but the bottom one is probably the most widely used situation. So continuing on here, we can discuss some of the convolution properties. So these are some things that you can use to help you think through some problems and understand how various scenarios in the real world might play themselves out. So the first property is commutativity, and it basically says it doesn't matter what you convolve, what order you do the convolution. X convolved with H convolved with X, both give you the same thing. And it's that property that allowed us to use both of those two forms, either of those two forms, depending on whether we flip X or flip H. Associativity basically says that if we convolve x first with v, then convolve it with w, that's the same as taking v and convolving it with w first and then convolving that with x. And so if we look at this second one, that would be the case where we might have x first going into some system with an impulse response v, and that convolution gives us the output of that system, and then that output is run directly into a system with an impulse response of w. That says that we could, if we wanted to, convert that cascade of two systems instead into an equivalent single system whose impulse response is just v convolved with w. And so that's what that one's saying. This one says that if we take x and convolve it with some system with impulse response h1, and take x and convolve it with an impulse response h2, and then add those outputs together, we could replace that scenario with just a single system whose impulse responses are the sum of the two individuals, and then take that single resulting impulse response and convolve it with x. And then the last one just says if you convolve x with some shifted version of the delta function, shifted by q, what you get out is the original input shifted by q. And so this last one is very easy to see, and I would encourage you to just try to explore that and understand how that works on your own. Okay, last slide of this set of notes. Just a few things here to tidy up at the end. So we've talked about stability. We talked about BIBO or bibostable. So we can actually show that a system is bibostable if and only if its impulse response is absolutely summable. So that means you take the absolute value, that's the absolutely part, you add up all the resulting numbers, potentially infinitely many of them, and that resulting number, if it's less than infinity, then the system will be stable. So notice that what this says is that in order for the system to be stable, bibo or bibostable, our impulse response needs to decay fast enough so that the sum is bounded. Not an easy way to check for stability, as we alluded to earlier in another set of notes. You should already know that the best way to look at stability is through looking at the location of the poles of the system. That's something that we talked about at length in the signals and systems. And then finally, to finish things up here, we'll talk about systems with infinite duration and finite duration impulse response. So this was our general result for a causal system, and we needed to go all the way up to infinity here. If we talk about, that's because in this form, we're considering the impulse response to go on forever. But if the impulse response actually goes to zero after some finite number of points, then we would call that a finite duration impulse response, or an FIR system. And for that case, it's pretty easy to see that we can then truncate this sum and only have to go out to the value of m minus 1. And in this case, we would be talking about an FIR system that has order m. And so we'll stop there, and I'll post this up on the web, and then I'll see you in the next video.